Exception handling. In this nugget, you're going to learn some really practical, useful skills in Python programming. I'm going to show you what exceptions are, and then we're going to really deep dive and understand how exceptions are manifested in Python programs. The bottom line is we want our deliverable, that is to say, our end-of-the-day Python application, to run without crashing. That's a given. Now, sometimes that's ideal rather than an actuality, but the more effort we put into exception handling, the more stable and better performing our application will be, and therefore the more satisfied our customers will be. In the second half of this nugget, after we gain our baseline understanding of exceptions, I'll teach you how to manually raise exceptions and then use Python's built-in try, except, finally structure to catch and handle those exceptions. Let's get to work. What are exceptions anyway? First thing I want you to know is that exceptions are not something that's localized to Python. Any programming language is going to have what are called exceptional events. In several of our code samples thus far in this CBT Nuggets training, we've run into cases where our procedural program works just fine as long as the user proceeds along an expected route. As a programmer, we're always looking for things that can go wrong in our code. Sometimes you have really common issues, like for instance if we're trying to open a web page or do file writes, file copies, and we have an input-output error. What if a file that was expected to be there isn't going to be there? Is that going to crash our program? Or taking input from the user and having it be in an incorrect data type or format. Or maybe your own syntax in your own code is incorrect. These are all cases that are normally going to halt the execution, or interpretation, as the case may be with Python, of your program. Programmers often talk of what are called edge cases as well. Now, we have the major things that can go wrong with most programs. These are just three representative examples, I/O, syntax, and incorrect data types. But you also really want to thoroughly unit test, that's another programmer term, your application to look for edge cases. Things that aren't going to go wrong with most of your customers using the program, but maybe the rogue customer off to the side who happens to turn left instead of right in that program, and the program halts, you see? So all of these exceptional events need to be handled in order for the application to continue running. Now, we've seen several times when we're working in the Python interpreter, for instance, what's called a traceback object. So as you see in this example, we're doing division by 0, which is always in Python going to raise a traceback. What's being traced back is what's called the call stack. We're going to define the call stack in just a minute. But basically, your procedural program trucks along a routine at a time, an event at a time, and if we run into an unhandled exception, the program is going to halt and a traceback is going to be generated that gives you, among other things, which line in the module is causing the problem, and then the specific exception object that Python has raised. In this example, zero division error is a built-in exception in Python 2 and 3. Some additional vocabulary that we need to be aware of are the following terms. When Python has an exceptional event happen, this is called throwing an exception or raising an exception. Now, you could really further differentiate these terms. Raise specifically is something that we as a programmer might invoke to make sure that exceptions occur on our terms. On the other hand, if Python interpreter throws an exception, at least in my personal experience, that's an exception that you were not expecting and may be unhandled, and you need to go back and address that. Speaking of handling, when an exception occurs, it's up to us as Python programmers to handle, catch, or trap those exceptions. Not just the main problems, but also edge cases as well. And once again, the Python standard library gives us a lot of built-in exceptions. Python 2 contained all those exceptions in a standard library module called exceptions. One change between Python 2 and Python 3 is that in Python 3, exceptions are now stored in the built-ins module. I would recommend that you truck on over to docs.python.org, look up the documentation library for your version of Python. Of course, I'm looking at version 3 here. And there's an article in that corpus called Built-in Exceptions. It gives you some really useful background on what exceptions are. Exceptions are class objects. Now, as you know, and you've come to expect in this training, we often overlap and sometimes foreshadow topics that we formally cover in future nuggets. That's going to be the case in this nugget because in discussing exceptions, we by definition have to talk about classes and object-oriented programming. This will be a nice wade on the shallow end of the pool that we're going to flesh in when we do our 2 nuggets on OOP. The article goes on to describe using try and except clauses, which we're going to do, so we don't need to discuss it now. And then finally come down to the actual exceptions in the standard library. The ultimate base class for your built-in exceptions in Python is called base exception. However, in practice, when we create our own custom exceptions, we tend to subclass from the exception built-in class. And then it just goes on here. You see EOF error, end of file error, floating point error, there's our friend IO error, import error, index error. All of these errors are pretty straightforward. They definitely bear you to study them to get more familiar with them though. Back in the Python interpreter, we can take a look at those built-in exceptions by running an import. Now, I'm in Python 3.1.1 as you see, so if I try to import the exceptions module, we're going to trace back immediately. The problem here is the import error, no module name exceptions. This is only going to work in Python 2. Remember, in Python 3, your exceptions are now stored in the built-ins module, so we can run dir against built-ins to get a list of all of the names. In particular, you see the list will always begin with your classes and then come into your methods. Many of these classes, if not all of them, are our exception classes. Arithmetic error, runtime warning. In fact, that brings up a good point. In this nugget, we're focusing only on exceptions as errors. There's a subset of those classes that deal with warning messages. The main difference between a warning and an error in Python is that warning will pop up but continue program flow. An error is something that will actually dead stop your application. So that's what we're focusing on in this nugget. One of many important design considerations for you as a Python software developer is where you're going to place your error or exception handling code. There's a term that you should be aware of called bubbling up. And what this means is that you might have within your larger application a particular function that has some possible grounds for exception, whether it's user-generated or whatever. And if you're not handling that exception within that modular unit in your code, that unhandled exception may lie dormant and eventually bubble up to a larger scope, even hitting the global scope of the application, which of course is going to fail the entire thing. So that's one thing to consider, this notion of bubbling up. What you see in this diagram is a graphic from wikipedia.org that shows the call stack. Call stack is a programming term that's certainly not specific to Python. Wikipedia defines the call stack as a stack data structure that stores information about the active subroutines of a computer program. So a stack literally like, I imagine, Legos. You're probably familiar with those, where you can stack them modularly, one on top of the other, and so on. As your Python program runs and you're invoking functions and instantiating classes and running methods, you're adding one by one what are called stack frames to that execution stack or call stack. Now that's useful again because, like I said, when you do run into an unhandled exception or even a handled exception and a traceback is issued, you may get important information that tells you, in fact you will get important information in most cases, that tells you which stack frame or specifically where in your code the problem lies. This is beyond our scope, but I just want to let you know that you can view stack contents in Python in several different ways. There's tons of third-party and a couple standard library modules that allow you to run traces, diagnostic debug traces on your code. The built-in module inspect has a stack function that reveals the current contents of the call stack. So I wanted to give you that just as something to consider. Alright, so now that we know what an exception is, and we know that Python includes a library of built-in exception classes, how can we start to use these? The first statement I need you to understand is the raise statement. We can use the raise statement interactively or in our code to manually generate an exception. Now you might be thinking to yourself, well, wait a minute. We don't want our program to generate an exception. Why would we do this? Well, you do this to be proactive. That is to say, in your program code, you're going along doing your tests, your while loops, etc. You can throw in strategically placed try and except blocks to manually raise a particular, let's say a custom exception class, and then run code that you want to run to recover or log or whatever you need to do from that exception. You see? dependency, so actually the raise statement gives you full control over how exceptions are generated in your Python program. Now, the main heavy lifting with exception handling is using the try except block. This is really the centerpiece of this nugget. The way try except works is that you wrap your code that contains the volatile procedure in there, and the way it works is if the code in the try block completes without generating an exception, you escape the try except block and continue going on with your program. If an exception is handled that's being caught by you, you then go to the except part of the structure. Now, I'll show you in great degree of detail how all the manifold except clauses work. You can generate an exception for a specific built-in exception. You can use your except clause to handle multiple built-in exceptions. And finally, you can use except to trap your own custom exception classes as well. Or frankly, you could just do except with no parameter, and any exception that's generated in your try block would be handled by your except block. So under the except clause, you would put your handler code. This could be providing feedback to your user. This could be writing log or diagnostic information, etc. Optionally, you have the finally clause. And what finally does is it's used for cleaning up when you're running a try and except. For instance, you might have in your try block a call to the open function where you're opening a file and appending to it. You could have exception handling such that if something goes wrong, say an I/O error, you can write a diagnostic message to let you know. And then in the finally block, you could issue the close function just to make sure that no matter what happens, whether this try and except completes without an exception or if it does have an exception, the file is always closed. So finally is run regardless of whether the try block completes successfully or not. That's an important note. And again, I'm just giving you the theory right now. We're ready to jump into a detailed demo where I show you how this works in living color. But first, let's take a look at this. The old or traditional programming idiom. Idiom is an expression that has a fuzzy or unknown origin. In programming terms, idiom is used a little bit more specifically just as an operating principle that programmers use. The old traditional idiom with programming is look before you leap. This idiom involves lots of testing in your code. We've kind of used this idiom a lot so far in our training in order to trap cases where an exception could be handled. Think of that number guessing game. We could have if the number is not an integer, do this, and so on. So this is a really conservative way to program, to look before you leap. In other words, try to capture as much exception grist on the front end as possible. A lot of times you can use if blocks. The problem with that among Pythonistas is that all those if blocks tend to clutter your code, make it much more difficult to read. And remember, the Zen of Python, we want our code to be as readable and simple and elegant as possible. Therefore, Python's idiom is it's easier to ask for forgiveness than permission. Again, a little tongue-in-cheek, but it does contain some true wisdom. In other words, we want to plunge ahead, not being completely reckless, because we do have try, except, and finally. But instead of being ultra careful and conservative with this look before you leap idiom, we're going to go ahead and try to do some work in our Python programming, and then if something goes wrong, we can take care of that with an except statement. We're going to start our demonstration from the Python interpreter, and more specifically, I'm going to show you how to use the raise keyword to manually raise a particular instance of a particular exception class. Now, one thing that you need to be aware of is that built-in exceptions are all capitalized, and that's in keeping with the general object-oriented programming suggestion that all of our class names be capitalized. Therefore, if I raise exception without capitalizing that name, we get a simple name error where Python basically says, I don't know what you're talking about. So we can raise exception, which is the base exception from which our custom exceptions generally flow. And in doing that, we get a traceback, of course, and it gives us the name of the exception. And what we're doing here when we raise is that we're instantiating an instance of the exception object. Now we can add additional text to a manual exception. Check this out. I'll say raise exception, and then I will pass in the flux capacitor is broken. And this raises an instance of the exception base class, and this time we're able to add a little bit more helpful information for the user. Remember how we looked at all of the built-in exception classes. We can import built-ins. I don't remember if I already imported it or not, so I'm doing it again. And then run dir to get a list of all of those standard errors. You can raise any of those directly, just again, by using raise with the class name, you see? Now let's switch over from the interactive environment and take a look at a script file that I put together. I have several examples. I'm just going to selectively uncomment them so we can run the code. In our first example, we're catching the instance of division by 0. So we're creating two names that fetch input from the user, first number, second number. You'll remember by now that input always comes back with a string object, so I'm converting that to int, and then we're printing our result as A divided by B. That'll work all day long as we're using legal numbers. So let's run this module. My first number is 10, my second number is 2, our result is 5.0. You'll remember with Python 3, it's doing float work with those numbers. Let's run the module again. First number will do 10.1, and look, we've already raised a traceback. It's a value error because the way we have our code, it's expecting a string, needs to become an int. 10.1 choked the code. But in this case, we're not worrying about that particular edge case. What we're concerned about is what happens if we do division by 0. So if the first number is 10, second number is 0, again, we get a traceback. So 1 is a value error if we use a float rather than just an integer. Second problem is 0 division error. So we're seeing instances of two built-in classes here, aren't we? So there's lots of grist for the mill as far as tightening this program and making it more user-friendly. Let's look at the second code block now. Here we're going to actually use try and except to capture a specific type of error. So you'll note that we open with try, and then we have our indented test, which is our creation of the A and B names, and then printing the result of that division. Now, as long as we put standard integers in our code, we're going to get back the expected result. In this case, though, if we do division by 0, we're going to handle that exception specifically, and we're going to print error division by 0 will not work. So let's again run the module. Legal numbers are fine. Let's try division by 0 now, and now you'll notice that the exception has been handled. We come back with error division by 0 will not work, but the program still does terminate. I'm going to show you shortly how we can keep the program alive in the case that we want the code to continue executing. In our next example, I'm going to show you how we can capture multiple exceptions. We have our try, then we have an except for 0 division error, and then an except for value error, and each one of those is going to print out a custom error message. Now there's different ways you can do this. You can actually comma separate multiple exception classes to be more robust and to save yourself some code. So you notice that my addition here says that if we get a 0 division error, we handle with this code. If we get value error or IO error, we get the second error. So let's run this code. We'll do our division by 0, expected there. Run the module again. We'll do a first number of 10, and then we'll put in an incorrect data type like spam. So we got the exception handled in the second case there, didn't we? You used an incorrect data type. Here's another example of catching multiple exceptions at once. We open our try as expected. Notice that I've made a minor edit here, that we're converting the input to float instead of int to give us some more flexibility there. And yet again, we're capturing more than one exception type. What I forgot to mention in the previous example is that if you're going to write a single except clause that catches multiple exceptions, you need to wrap those in parentheses. That actually accomplishes a couple things. On one sense, remember we talked about order of operations earlier in the training, and I said that using parentheses is a really nice way to be more specific in your expressions, so there's that. But also when you bundle your exception classes together like this in parentheses, Python treats this as a tuple object. Okay? So in this case, we're capturing any of the three types and giving them this response. Now I'm showing you these different ways to go. The previous example had multiple except clauses that did something different depending upon the type of exception raised. What you're seeing in this particular example is kind of a catch-all bucket where we're doing the same remediation for several types of exceptions. Now, what you actually code in your programs is going to be dictated by your business needs. All right? I'm just just showing you the different ways to go here. Next, let's print some more dynamic exception text. It's one thing to just print a literal string. It's another thing to gather some traceback information from that standard exception class and give that to the user in addition to any of our programmer-defined static text. So after we do our try here, if we run into either a zero division, a value error, or a type error, we're using the as keyword to alias this condition, this exception condition, as a name called E. That's pretty standard. You can use any name here, but E is the standard one that most people use. And then in this exception handler, I'm simply printing the static text, the string literal error, and then space, and then the value. So let's run this program. We'll do a first number of 10, second number of 0, and it tells us error, and then it gives us a little more. This isn't particularly helpful here. It just says float division, but it gives us the specific error that comes from Python. Let's try if we use an incorrect data type. If we do that, we get a little bit more helpful data. Could not convert string to float, spam. The question you've probably been wanting to ask for the past few minutes is, well, it's nice that we can catch these exceptions when they come up, but still, all we're doing really is providing meaningful feedback to the user, and the program itself aborts. What are some ways that we can keep the program running after an exception occurs? Well, one method that will work all the time is to open up a while loop, and we could use while true as a way to open the loop and keep it open until the condition inside the loop becomes false, okay? We do have to remember that in order to use the break and continue keywords, that we have to have either a for or a while loop going. So that necessitates our opening up a while loop here. So after our try, we have an except. And here I'm doing something pretty broad brush, and you may not want to do this in your code, except with no exception classes listed after it means that any kind of exception, no matter what it is that occurs during the try clause, gets shuttled down here. So we're just going to print invalid input, please retry. Because we're familiar with how while loops work, this exception handler, after the user gets invalid input, please retry, is now going to go up to the top of the while loop again, and we're going to try this block again. You'll also recall to finish up that the way to get out of a while loop is to put in an else. Else is just including break here to break us out of the entire loop structure. And what that's going to have the effect of in this little program is once we put in valid data, once this try actually works and we skip the except, the condition in the while loop is no longer true and will break the program. So we'll run the module. First number I'll do 10, second number I'll do 0. We've handled it. We're now given an opportunity to retry. I'll do 10. I'll give a bad number, or bad data type rather. Finally, if I put in the correct data, we get our result and the program breaks. Well, it ends successfully, let's put it that way. For our final example, before we get back to the whiteboard and complete this nugget, let's take a look at the finally clause to clean up after an exception handles. Strictly speaking, the finally runs regardless of whether an exception occurs. That's something that some Python newcomers forget or overlook or just aren't aware of. That is to say, in our function declaration, divlog, that's going to take two arguments, x and y, and very simply divide y into x, we're going to try to open up a file for appending. So we'll be able to run this function multiple times and not overwrite any data that's already in this file. And then we're going to write a line to that file that gives us user-friendly representation of whatever arguments we've passed into divlog. Now you should remember the format method and the Python 3 style string formatting, where in the braces we can use positional numbers 0, 1, 2, and then as arguments to the string format method, we can substitute in this case, we're substituting x, and then we're doing a / to denote division, y equals, and then the result is going to be the third element here, x/y, which means x divided by y. So that's going to be, and the new line, of course, gives us a carriage return, so to speak, so that as we do this, or as we run divlog function multiple times, we're going to get multiple lines added to our file. Now we're capturing 0 by division here by writing a line to this divlog.txt file that says error 0 division not allowed and gives us again a new line. Raise here is formally optional, but I'm throwing it in here just to make sure that we're raising a formal exception. And then finally happens regardless of whether the try completed successfully or if we have a 0 by division error. Now you might wonder, well, what happens if another kind of error happens? I don't know if I've formally described this to you. Well, if we have an unhandled exception, then the program's just simply going to abort. Remember, the reason why we're doing exception handling is to try to think of every exception class that might be raised in the running of your program and make sure that you have some code or some routine to respond to that exceptional event. Regardless, though, we want to make sure that the file is closed, because if Python has divlog.txt locked open, we're not going to be able to access it from the operating system or from another program, you see. So f.close is a good way to wrap up this function regardless of whether it completes successfully. Let's save our changes. I think the best way to handle this is to come over to the Python shell and let's run import of exception2. I'm going to run dir just to show you we have our private or magic methods, and then at the end of that list we have any user-defined functions. Of course, we have divlog. The way we're going to test this is we're going to call the divlog function 3 times right in our module here. You'll notice that 2 of the 3 calls are valid. We're providing valid arguments, and then in the third one we're going to do a division by 0. Let's see what happens. Now the program bailed with a traceback, of course, because remember, the error handling code we included in the program did not suppress this, so we shouldn't be surprised to see this at all. But what we should see if we go out onto the file system, in particular into this path, cfiles divlog.txt, we should see that the file exists, which it does, and we should see 2 successful string formatted lines, 100 divided by 21, 20 divided by 5, and then our third one that included the 0 division, printed this log entry, and closed the file. Proof that the file was successfully closed is evidenced by the fact that I'm able to open it with no problem here from the Windows operating system. Creating custom exceptions. Everything we've done thus far in this nugget presupposes that we're catching exceptions that are part of Python's standard library of exception classes. However, you need to understand that you can create your own custom exceptions and invoke or raise those custom exceptions to do whatever you need to do in those cases, okay? Now, the way you create a custom exception is by subclassing any of the standard library exception classes. Now, what the heck do I mean by that? If you've already jumped ahead and watched our 2 nuggets on object-oriented programming, then you're already aware of this. But if not, I'm going to give you a little tease, as I promised at the opening of this nugget, in object-oriented programming, and you see how this works, and then by the time we get to those nuggets, you should be all set, really. Here's the deal. A class is like a blueprint. That's how it's traditionally introduced to new students. You can look at it like this. I'm in Microsoft Word, and we could look at the templates that come with Microsoft Word as classes, such that if I do a file new and then take a look at the built-in templates in Microsoft Word, like business facts, all of these are, in a sense, classes. As you know, using templates in Office productivity applications, these are pre-formatted. They have their own custom page margins, their own fonts, their own heading styles, perhaps embedded graphics. We can draw an analogy to Python that we have different classes or templates that include their own properties, which define characteristics of that class, as well as methods, which, as we previously explained, are nothing other than functions that are attached to a particular object. Now, when I'm creating a new document in Microsoft Word based on one of these templates, I click OK, and I'm not opening up the template or the class itself. I'm instantiating or creating an instance of that template. The original template is untouched, okay? Similarly, in object-oriented programming in Python, we can create a custom template based on one of Python's internal libraries of templates. Now, why would you want to do that? One great benefit is that by subclassing from, say, the exception class, we are saving ourselves a lot of work and taking advantage of all of the built-in properties, variables, and methods that are attached to that exception class. There's 2 words that are in object-oriented programming that are important here: encapsulation and inheritance. By creating a custom class that inherits from an already existing class, again, to repeat, that means we then have immediate access to all of the properties and methods of that class from which we're inheriting. That also means that we can make changes to the base class, and if we want to, we can have our custom subclasses inherit those changes. Now, you don't always want that to happen in practical speaking, but that's how inheritance works with object-oriented programming. Encapsulation means simply that your class has properties and methods that kind of ride herd with that class and are always available using the dot notation that we've worked with before. I want you to know that you can subclass any of the Python built-in classes. Exception is used as kind of a generic blueprint, but if you want to create a custom I/O error handler, you might want to create a custom exception that inherits from I/O error, you see? It's simply at least two lines of code to create your own custom exception. In a sense, it's fabulously easy. You simply open up the interpreter if you're just working in memory, or open up a module file if you're creating a library. You use the class statement, and then you give the name of your custom class. Traditionally, as I said earlier, class names are put in what's called camel case, such that the first significant letter of each word in that class is capitalized. And then in parentheses, we pass in the class from which we're inheriting. Like I said, in many cases, you'll want to start with the exception base class. In this most simple of examples, again, we have colon, so we've got a header and a suite. In this most simplest of examples, we're just using the built-in Python pass statement. We haven't talked about pass thus far, so now's a good time to do it. You'll often see the pass statement included in sample code. Or as you're testing, as you're developing your application, you might know you need a class, but you're not ready at that time to develop specific code for the class. You can simply include the pass statement with nothing else, and that keeps that class function method alive. It's going to run just fine, but it won't do anything. Pass is kind of a null operator in a class method or function, okay? It's a really good keyword to have in your tool belt, though. Once you've built your class, it's just a question of calling it in your code. Now, you know how module imports work by now. You'll need to import the library that contains your custom exception classes, but in your code you can manually raise the class by using the raise keyword. In this case, we could say raise custom error and then put in some custom help text with that if we want to as an argument. We also know that we invoke exceptions with raise. In order to check for our custom exception, we would use try except finally as usual. In other words, I need you to understand that everything we've learned in this nugget with regard to raising and catching exceptions applies to your custom exceptions just as much as it does to the Python built-in ones. This final demonstration touches on creating custom exception classes in Python. This first one I'm going to do in memory from the Python interpreter. We'll use the class statement with the name of our class. Remember, camel case is the convention. I'm going to inherit from the exception built-in base class. And as I showed you in the previous whiteboard, I'm simply going to pass or make this a null activity in the event that this class is instantiated. Speaking of instantiating an instance of this class, I'll now use raise to bring up custom error, and we'll pass in a string literal, something went kerflunky. By the way, kerflunky is the technical term for when something goes wrong. Just kidding. It happens to be one of my pet words, though. So as expected, we get an immediate traceback that gives us our raise as well as our help text. Almost as prevalent as hello world when you're looking at the documentation for a specific programming language, it seems that the generic boilerplate text for creating your own custom exception in Python almost always boils back to this example that I've adapted from docs.python.org, their own documentation. In this case, I'm creating a module, or I've already created a module called customclass.py that contains our single class definition for a custom exception called myError. Now, again, we're hinting at some of our object-oriented stuff here. Hang with me now, it's not all that difficult to understand. Formally speaking, when you're doing object-oriented programming and you're creating a class, you're going to want to include as your very first element in that class declaration a function called init. This is, again, one of those magic names, double underscore name, double underscore. And what this line does is it's a constructor. And a constructor is code that actually is the engine for creating an instance of that given class. So we'll do def double underscore init double underscore and then any input parameters that you need. The first one in Python is always going to be self, and then you would do any supplied, user supplied arguments. In this case, there's really only one argument, value. Self is private and internal to this function in this class definition. Almost always when you build a class, exception or otherwise, you'll also want to invoke the str magic function. Str provides, as you know from using the string function in the interpreter and in our code in earlier examples, gives us a string representation of a given object. So what this is allowing us to do is if we run the string function against an instance of the myError class, instead of just giving you the really unhelpful information of basically this is an object of myError, we're returning a representation. REPR is a much more accurate string representation than str is of self.value. By the way, I forgot to mention that in our constructor declaration, we're creating one variable called self.value, and that's going to be the value of our input parameter or argument value. So if we run str myError, we're going to come back with whatever was given by the user as value. In the remainder of this module, we're running a simple try except block where we're going to raise myError, and the value that's being passed into this instance is 2 times 2. This is really toy code because, of course, in raising myError, this except statement is going to be executed, and what we're doing in this toy code is capturing myError as the name e, and then we're printing back myError occurred, the value is e.value. Let's run this module, and of course the error occurred. The value that was passed into the class constructor was 2 times 2. The value is 4. Exception handling review. In this nugget, we formally introduced and performed a deep dive technical overview of exceptions in Python. I feel good about the fact that if you're clear and comfortable with what we've covered in this nugget, you should be quite a bit down the path in your learning curve as far as raising and catching exceptions in your Python code. You'll also be pleased to understand that exception handling in other languages like C#, Java, and so on functions very much the same way that exception handling does in Python. This deals with Python's flexibility as both a procedural and an object-oriented programming language, and the bleed over that you get with those general principles, polymorphism, encapsulation, inheritance, etc., among all OOP schemes. I hope that this has been informative for you, and I'd like to thank you for viewing.